Hello friends, this is the Science Chef again. In this video, we'll be learning about the definition and properties of bases in the second part of a series on acids, bases and salts. Go nowhere, I will be right back after this break. If you'd like us to make more of these tutorials, like this video, subscribe to our channel and turn on your notification bell. If you'd also like to watch our last tutorials on the definitions and properties of acids, check the link in the description. Generally, a base is any substance that turns red litmus paper blue and neutralizes an acid. However, just like acids, bases can also be defined based on the Arrhenius, Bronsted-Lowry and Lewis concepts. An Arrhenius base is a substance that dissolves in water to produce hydroxide ion as the only negative ion. In other words, Arrhenius bases are alkalis because alkalis are soluble hydroxides which dissociate in water to form hydroxide ions. Examples of Arrhenius acids are sodium hydroxide, potassium hydroxide, lithium hydroxide, calcium hydroxide, barium hydroxide, and ammonium hydroxide. A Bronsted-Lowry base is a proton acceptor. In other words, any substance that can accept a proton in a reaction is said to be a base. This definition agrees with the Arrhenius concept, as the hydroxide ions produced by the base can combine with a proton from an acid to form water. Therefore, it is safe to say that Arrhenius acids are Bronsted-Lowry acids. Other examples are metallic oxides like copper 2 oxide, magnesium oxide, zinc oxide, aluminum oxide, and insoluble hydroxides like magnesium hydroxide, also called milk of magnesia, zinc hydroxide, aluminum hydroxide, etc. A Lewis base is any substance that can donate a pair of electrons to an electron deficient center in a reaction. Based on this concept, anions with excess electrons like chloride ion, hydroxide ion, cyanide ion, or neutral molecules with lone pairs of electrons like ammonia, water, ethylene diamine that can donate a pair of electrons to a central metal ion in a complex ion are examples of Lewis bases. They are also called ligands. Just like acids, bases can be classified in terms of their strength into strong and weak bases. Strong bases dissociate completely in water, while weak bases dissociate partially in water. Sodium hydroxide, potassium hydroxide, lithium hydroxide, and barium hydroxide are some examples of strong bases and are also said to be strong alkalis. Meanwhile, calcium hydroxide, magnesium hydroxide, aluminum hydroxide, copper 2 hydroxide, and ammonium hydroxide, also called aqueous ammonia, are examples of weak bases. Calcium hydroxide and ammonium hydroxide are also weak alkalis. Refer to our last tutorial on definition and properties of acids to learn how to identify complete and partial dissociation. Now let's look at the physical properties of bases. An alkaline solution is colorless with a bitter taste and is slippery to touch. The slippery nature of soaps is partly due to the presence of sodium hydroxide or potassium hydroxide used as the major ingredient. A dilute alkaline solution turns red litmus paper blue, while a concentrated alkaline solution is corrosive. Just like acids, soluble bases conduct electricity in solution. Strong alkalis are strong electrolytes, while weak alkalis are weak electrolytes. Next is the chemical properties of bases. A base exhibits two major chemical properties, which are 1. Reaction with acids to form salt and water in neutralization reaction. We will learn extensively about neutralization reactions in our next tutorial. Examples of reactions of bases with acids are ethanoic acid and potassium hydroxide to form potassium ethanoate and water, hydrochloric acid and copper 2 oxide to form copper 2 chloride and water, and nitric acid reacting with aqueous ammonia to form ammonium nitrate and water. Ammonium nitrate is a good fertilizer rich in nitrogen. Next is a reaction of alkalis with ammonium salt to form salt, water, and ammonia. Whenever an alkali is added to an ammonium salt and warmed gently, ammonia is liberated as a colorless gas with a choking smell, which turns damp red litmus paper blue. This reaction is used as a test for identifying bases or ammonium ions. Usually, the first stage of the reaction involves the formation of ammonium hydroxide. On gentle warming, the unstable ammonium hydroxide decomposes to water and ammonia gas, which turns the moist red litmus paper blue. Note that if the paper is not wet, the gas will have no effect on it. This is because without dissolving in the moisture, the ammonia gas cannot form the hydroxide ion that will change the color of the litmus paper. Examples of such reactions are reaction of calcium hydroxide and ammonium hydroxide to produce calcium chloride, ammonia, and water. This reaction is commonly applied in the laboratory preparation of ammonia gas. Also, sodium hydroxide can react with ammonium sulfate to form sodium sulfate, ammonia, and water. Likewise, ammonium nitrate reacts with potassium hydroxide to form potassium nitrate, ammonia, and water. As I stated earlier, our next tutorial will be on neutralization reactions. Subscribe to our channel and turn on your notification bell to get notified when we publish the video. Until then, stay on top.